Welcome back, ladies and gentlemen. In this short video, I'll be doing the preparation for Chapter 18, Practice C. And so here we're going to be looking at equivalent resistance. That's the word, equivalent resistance. So as I mentioned to you in the last video, a battery only just sees a resistor or a resistance, in other words, being impedance. So we're going to look at number 23. It says, find the equivalent resistance of the circuit shown in the figure below. So we have to look at this circuit here and analyze it. Because remember, here's my battery. The short one is the negative terminal, and the long one is the positive terminal. Because usually I just put plus and minus in a circle. It's another way. So this power supply or battery only sees one effective or equivalent resistance. We need to figure out what that is, knowing what we know about series and parallel. So I look at this and I can see that the 18 ohm, the 9 ohm, the 6 ohm, those are in parallel. Okay, so all these look like they're in parallel, just the 18. How do I know that? Because this node is the same as this node, and this node is the same. So all the 6, the 9, the 8 are all connected to the same node right here. These blank lines could just be all smushed together. And the same thing on this side, they're all connected. So I know that here 18 ohms is in parallel with 9 ohms, which is in parallel with 6 ohms. So let's just reduce this portion down into its equivalent resistance. So this part right here, I'm going to say, I'll put R equivalent 1, because we're going to have another one. So R equivalent 1, well, actually the inverse of R equivalent 1 is equal to 1 over 18 plus 1 over 9 plus 1 over 6. And I remember doing one just like this in our homework because they all have the same denominator of 18, so you don't have to use a calculator. We'll use a calculator here this time. I'm going to have the inverse of 18 plus the inverse of 9 plus the inverse of 6. And I get 37 over 16. Did I do this right? Oh, look, I didn't. I did 6 instead of the inverse of 6. Okay, try this again. All right, 18 inverse plus 9 inverse plus 6 inverse. There we go. And I get 1/3. So this is equal to 1/3. So that means that R equivalent 1 is 3 over 1, 3 ohms. So if I collapse, I'm going to put these all in yellow. If I collapse these all down into 1, it's just really a 3 ohm resistor. So let me redraw this whole circuit with this being the 3 ohms. I'm going to use my favorite here. This is 30 volts, and that's connected here to a 12 ohm resistor. 12 ohm resistor, and now it's connected in series with 3 ohms. 3 ohms. There we go. So I just redrew the circuit. I redrew the circuit. All these three, I collapse it down to its equivalent. And then I notice, these two, the 12 and the 3 ohms, share one node. Right here. They share one node. It means that they're in series. So I can replace this with these two being in series. So I'm going to replace that. I'm going to say it's 30 volt connected to one resistor. Just one resistor. Well, what is the equivalent of 12 ohms and 3 ohms in series? Remember, if they're in series, you just add it up. So I'm going to show you my handout to remind you here. If they're in series, we just add them up. If they're in parallel, the inverse of the equivalent resistor is the sum of the inverses of the other of all the resistors that are in parallel. Okay, so I have a 12 ohm and a 3 ohm in series. I just add them up. So 12 plus 3 is equal to 15 ohms. So this is 15 ohms. So that's my equivalent resistance. Is 15 ohms. Now, if you wanted to know how much current is being delivered by this power supply, the battery, how much current is going into and out of the battery. Did I do that right? Nope, the other way around, from positive to the negative. All right, so the current's going this way, from the positive to the negative. I'm getting myself confused here. Anyway, the current, the magnitude of the current, we have V is equal to IR. So I is V over R, and we're talking about the equivalent. So we have 30 volts and 15 ohms. 30 volts and 15 ohms. And 30 15ths, 15 times 2 is 30, so I know that I is exactly 2 amps. So this battery is supplying 2 amps to the rest of the circuit. So see here going, yeah, I was right, plus minus. So it's going this way, goes from the let me write it here. Yeah, from the minus to the plus, minus to the plus. Okay, so I was right the first time. The current's going towards the plus. Anyway, the current is going, so I have 2 amps coming into the battery, 2 amps coming out of the battery. So that means that the 2 amps must have come out from this 12 ohms resistor as well. When it gets on this side over here, it's going to split up. Some of it's going to go through the 18 ohms, some of it's going to split up to the 9 ohms, some is going to split up to the 6 ohms. And all I know is that the voltage across all 3 is the same because they're in parallel. Okay, so again, what did we do for this circuit? All we had to do was analyze it and recognize that these 3 were in parallel. So because they were in parallel, I figured out that the equivalent resistance of these 3 in parallel was 3 ohms. So I had a 12 ohm in series with the 3 ohm, which I redrew right here. Well, I know if they're in series, I just have to add them up, and 12 plus 3 is 15. So the answer here is the equivalent resistance is 15 ohms. There it is, 15 ohms. All right, let's take the next one. Last one here. Number 24. Even more fun. Number 24. It says, find the equivalent resistance of the circuit shown in the figure below. So now we have a few more things, and you have to look and say, what's in series and what's in parallel? So I have a 12-volt battery. I have 7 ohms. And then here it gets split off. I have 7 ohms this way, and I've got 7 ohms this way. And then I have the 7 ohms in series with this 7 ohms. How do I know that this resistor is in series with 7 ohms? Because it shares one node. There's nothing else between them. Okay, so let me take a look here. Is the 15 ohms in series with the 7 ohms? No, it is not, because this node has something else hanging off of it. Okay, so here there was nothing else between them. So if these 2 are in series, then let me redraw them so that these 2 are in series. And if they're in series, I just take 7 ohms and I add it to 7 ohms. All right, so let me redraw that. Redraw that. I'm going to have my 12-volt battery. I have a 7 ohm resistor up here. I have a 1.5 resistor down here. Okay, and then I have a 7 ohm here, 7 ohm. Now, that's 7 ohms. Now, these 2, I notice that these are in series. So if you can imagine this node and this node, see how this 7 node and the 7 node, they both are on either side of this particular 7 ohm. There's too many 7 ohms. Let me tell you what I mean here. Okay, this 7 ohm is this 7 ohm right there. The top of this 7 ohm is connected to this, I'll call this one top, and this one's the bottom 7 ohm. But this one and this one, these are in series. So I can add these 2 and say they're 14 ohms in parallel with this guy. So let me redraw that. So my 7 ohm top and my 7 ohm bottom, that one became 14 ohms. Okay, so what did I do here? I took this one, and I realized that they're in series. So that one is this one right here, the 14 ohms. Now that I redrew this, I realized, oh, look, the 7 ohms and the 14 ohms, those 2 are in parallel. So I have 7 ohms in parallel with 14 ohms. So I'm going to redraw just this part and stick that in the circuit. But first I need to figure out what that is. So I'm going to say 1/R equivalent for this part here. It's not the equivalent, so I'll put equivalent prime, the first prime, is equal to 1/7 plus 1/14. So let's figure out what that is. Okay, clear. So the inverse of 7 plus the inverse of 14 is 3/14. 3/14. So the inverse of that, so I'm going to call my R equivalent prime and take the inverse of that. That'll give me 14 thirds, which is, press the button, 4.666666. I know it's 4 2/3. So I'm going to say 4 2/3 ohms. 4 2/3. That's just more precise than 0.67. 4 2/3. So now I'm going to redraw this circuit again. Let's see, I'm going to redraw it down here. Where can I redraw this? I draw it right on this side over here. So now I have my 12 volts. And that one has a 7 ohm up here, 7 ohm. And on the bottom, I have 1.5 ohm. All right, now I have this 7 ohm and 14 ohms together. I figured out that together these are in parallel. I can replace that with its equivalent, which we just figured out was 4 2/3 ohms. Now I look at my circuit and realize, oh look, the 7 ohms is in series with the 4 2/3. They share one node. And the 4 2/3 is in series with the 1.5. They're all in series. I'm going to write these are in series now. And I can just add them all up. So I'm going to redraw this with a 12 volt battery and 1 resistor. And this one's going to be the 7 plus 4 2/3 plus 1.5. And let's see what that is. Let's see, I'll leave that in there. 4 2/3 plus 1.5 plus 7. And I get 13.1666667. So it's equal to 13.16667 ohms. And what did it ask for? It asked for the equivalent resistance. Equivalent resistance. All right, so from here then I can say equivalent resistance is about 13.2 ohms. 13.2 ohms. But before we leave this problem, I'm going to ask you, what is the current that's being delivered from the power supply? What is this current that's coming minus to plus this way, minus to plus? The current that's coming out. Well, let's figure that out. V equals I, our equivalent. So I is V divided by the voltage divided by the equivalent resistance. And the voltage is 12 volts divided by this 13.16667 ohms. I'm going to leave that here in my calculator. Oh, it's downstairs. So I'm going to take the inverse of it and then multiply by 12. I take the inverse of that times 12. And I get exactly 72/79. It's so funny that it does that for us. All right, and what is that? I hit this button, right? There we go. 0.911 amps. So we have to just say two significant figures, 0.91 amps. And that's the current that this power supply is delivering. So let's take a look at this again. In summary, this was the circuit that they gave us, and we have to analyze it and recognize that these outer 7 ohm, the top and the bottom, are in series. Well, if they're in series, then I can smash them together, add them up, and I did that. And they're 7 plus 7, 14 ohms. Then I recognize, oh, look at that. From here to here, it's in parallel with the pink 7 ohm resistor, in parallel to the 7 ohm resistor. So then I figure out the equivalent resistance of 7 and 14. 7 and 14, the reciprocal of them, and it was 4 2/3, or 4.66667 ohms. So then I replaced it with that one and redrew it here, replaced it. And I recognize that all 3 of these now are in series to each other. If they're in series to each other, all I have to do is add them up to get the new equivalent resistance. Okay, so this is a equivalent resistance, the final equivalent resistance. So I add them all up and I get 13.2. So that is my equivalent resistance, short for equivalent. And then I want you to also realize, therefore I can figure out how much current is coming out of, from, supplied to the rest of the circuit from the power supply, the 12 volts. And that's it. In the next one, we'll be talking about exactly now going backwards and figuring out how much exact current is going through each of these resistors and how much voltage is across each of the resistance. We say across because there's a voltage drop from one node to the other node. Okay, just like there's a voltage drop across these nodes right here. All right, so take a look and make sure you can recognize the resistors that are in parallel to each other and which resistors are in series with each other. And so we'll see you next time.